after I leave college, I can't get it because it's on my home computer. It's on my computer in my office, and then I forget to go back to that email when I get back. So just come to my office, and I can give you a printout. Yeah. So 5-3 number. 33. Oh, somebody else asked me about this earlier. 33 says 10 P's. This is page 221. So it says 10 P's are generated from parents having the green-yellow pair of genes. So if any of you guys have had biology any time in the past, you might know it's talking about good old Mendelssohn. They talk a little bit about it in the book. There's a 0.75 probability that a pea will have a green pod. Is it unusual? So find the probability that among the 10 offspring peas, at least 9 have green pods. So what the probability of at least 9? So what's wrong right there? I mean, the biggest mistake I see people do is they set up the problem for 9, and then they give me that as the answer. This doesn't say exactly 9. This is at least 9. And what does at least 9 mean? It could be 10 or 9, right? So you got to do both probabilities. It's an or. There's kind of an inherent or in here, isn't there? At least 9 is 9 or 10. So I have to add those two probabilities, right? So how would I set a probability of 9? What's my n in this case? How many things do I have happening? I have 10 P's that could be green or yellow. So there's 10 things. What's my probability of success? In this case, the success would be finding a green pod, right? So it's going to be 0.75 chance of success. So what's my chance of failure? 0.25. So how would the probability of 9, what would that look like, the setup for the equation? 10, choose 9. I've got 10 P's total. I want to choose 9 of them to do something specific. So how many do you want to do to be green successes? 9. And how many do you want to be failures? 1. It's got to be 1, right? So anybody who wasn't here last class, that didn't make a damn bit of sense. I understand. So got to kind of catch up. But basically, this formula right there, to have 9 exact green pods. It could be green, 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 and the last one is yellow. Or it could be green, green, and then the second to last one is yellow. But they're all going to have something in common. They're all going to have 9 greens and 1 yellow. How long is that list going to be? Which part of the equation tells me how long that list will be? 10 choose 9. It tells me the number of ways to do this. So every probability looks like that, and there's this many of them. I want to add them all up. That's exactly what this formula does. It adds up all of these possibilities. Right? So to put that in the calculator, I'll show you the shortcuts here. We would say 10 math over probability. Choose is number 3. 10 choose 9 times 0.75 to the 9th times 0.25 to the first. You want to do that. There it is. 0.1877. So you guys go ahead and do the situation for probability of 10. Try that out. Set up that equation, see what it comes out to be. Yeah. Sure. So for the first one, it would be 10 math. Right, the math button right there. Go over to probability, PRB. So arrow over to the PRB. And the third option is choose, NCR. 10 10, choose 9. And then just put the rest of it in there. Times 0.75 to the 9th times 0.25 to the 1st. You should get that. So I'll show you the shortcut after you guys do this one.
You want the answer?
Oh, let me see. How do you set up this equation? What would it look like? 10, choose all 10. So how many successes do you want? 10. And how many failures? 0. The funny thing is, this is going to be just this. Because how many ways is there to choose 10 things if I have 10? There's one way to do it. You choose all 10 of them. That's the only way you can do it. So this is 1. Anything to the 0 power is 1, right? So the whole thing's going to be dependent on this. So if you put the whole thing in, you're still going to get... So put the whole thing in if you wanted to. Here's a cool thing. Watch this. If it's second enter, I've done this a couple times. It'll bring back up the last thing. I just have to go up and adjust my stuff here, right? Insert a 0 for 10. Make this 10. Make this 0. Crap, Jen. Oh, yay. Well, that's simple, isn't it?
It's 0.25 0 and not equal 1.
There you go. Say again?
Say 0.25 is not equal 1 time 1 only.
How do you mean? 0.25 to the 0 power is 1.
Is that's the 0.75 time 10 power, right? And time.
Yeah, 0.75 to the 10th power times 0.25 to the 0 power.
It's just time. Can we put on a time 1 only?
Yeah, you know this is 1. Sure, and you know this is 1. If you put the whole thing in, it'll still come out right because it's just multiplying by 1. Yeah. So you get 0.0563. So what's the answer to the real question up here then? What do you have to do? Add those two together. Probability of at least 9 is 9 or 10, or means add. So this plus this. So 0.1877 plus 0.0563 is
24. 2.244.
244? Cool. So on your calculator Bible, I actually do put down there the shortcut to this. So if you want to. I'm still going to want to see your setup for the equation, but it's kind of nice to be able to check it very quickly. If you go, see right above where it says vars, and that really stands for variables. Right there it says vars. Right above that it says DISTR, distribution. And this is all about a binomial distribution. Right? So if I hit second, no Jeff, second vars, I get in here all these distributions. Look what I got up here. Normal distribution, inverse normal. I got some weird ass shit down here. We're going to learn about t-distribution in chapter 7. Chi-square is the thing that we do at the very end of the class. But if you go down far enough, here's your binomial, right? The difference between these two is binomial P is particular. When I want exactly something, binomial C, holy crap it has. I came a little early. Binomial C is cumulative. It'll add from 0 up to something. How are we doing? Semi-okay. So if I do binomial P and I put a 7 in there, it's going to calculate the probability of exactly 7. If I do binomial C and I put a 7 in there, it's going to calculate from 0 up to 7 and add all those probabilities up. Right, so it'd be like at most 7. So here I could just do Binomial Pdf. And the inputs for this are n, p, x. Because that's the only three things I need to know. Why do I not have to tell it q? Because it can get q from p, right? 1 minus p is q. 1 minus 0.75 was 0.25.
So how do you enter it?
Here we go. So you put n, what's n? 10, comma, and I see why you have punctuation in your calculator. 10, comma, p. What's the probability of success? 75%, good, 0.75. comma, the number of successes I want. Let's just do this one. Let's check the 9 one out. Put in there 9 successes. Enter.
Shortcut.
Shortcut. Cool. All right. Not good enough to just say I did this in my calculator. No, I need to see the setup of the formula. The calculator really just does that formula. It just puts it in and does it. So it hides what it's doing, right? But it's a good way to check yourself. So if you wanted to do 10, I could just hit second enter and go back over to 9 and make it a 10. And there's my 0.0563. Cool. So again, really good to have a way to check yourself. It's not good for learning because it doesn't show you what the hell it's doing. But it's a nice way to check yourself. How we doing? Yeah.
Can you show us how to get back to the Binomial Pdf?
Oh yeah. So go to second vars, because above that it says distribution, D-I-S-T-R. And then you have to scroll. You can scroll up to get there a little bit quicker because it's way down at the bottom. And there's something called the Poisson Distribution, and there's something called the geometric distribution. We're not really going to talk about those too much, but they do exist. Oh,
Sorry.
thank you.
Thank you.
And that earthquake thing's happening Thursday.
Yeah, some people said it today, but it's Thursday.
Thursday, yeah. Some people like me, yeah.
Okay, thank you.
Sure.
Have a nice day.
You too. Okay. So that's kind of nice to know that. There was something actually from chapter 5 I wanted to show you real quick before I get really back into doing some new stuff. Remember chapter 5 was all about, I think I might even have some data in here. Yeah, good. So this is a problem I think we did in class a while back. Let me see if it makes sense. 20, 61, so yeah. So if I add up L2, remember this would be my x's, and this would be my p of x's. So how did I just make sure that's what it was? I added these up and I got 1. So thank God. So I know that's what that is. Can anybody point out to me, where's my data? Where's my data at?
L1.
It is sort of L1, but not by itself. If you said just L1, then I got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And the average would be 3.
That tells you how many.
Beautiful. So my data is here, right? I still only have one variable. That could be the number of TVs somebody has. You know, somebody has 1, somebody has 2, whatever, right? It's still just one variable. So here's a shortcut for this. If I go do one var stat, so we've done that before, good old one variable statistics, but I have to tell it, oh, it's in L1, comma L2. Then it actually gives me the mean and the standard deviation. I can kind of double check myself for chapter 5, right? For section 5.2. Okay, so that's a nice thing. You've got to put it in there anyway to make the tables. You might as well do a quick one var stats L1, L2. You can double check what you get for the mean and the standard deviation. Okay, cool. Let me see. Any other questions from homework? No, okay. I'm an optimistic fool, so I take that as a good sign. What I want to do is to give us something to look at to help us transition into the next chapter. And this deals with, and it's a nice way to kind of review binomial stuff. Alright, so there are things in here that look familiar. The very first part of it should look very familiar because it's the last thing we did. I want you to take a minute and actually do those first 3 little problems at the top of the page. So for flipping a coin 14 times, obviously if it's a fair coin, I should expect half the time heads, half the time tails. So probably success here is 50%. So go ahead and try to figure out the probability you get exactly 9 heads, the probability you get exactly 1 head, and the probability you get more than 1 head. It's going to be a little bit tricky. You got to be careful on the last one. So try to do those right now. Try to set up the formula and maybe check yourself with the binomial Pdf thing we talked about. Yeah.
I calculate your guys can do this.
Neato.
It's the same thing, but what is this
So
going to be your n?
That's your n, yeah.
This is going to be
Your number of successes.
Okay.
So like the number 1 would be 9 successes out of 14 trials.
so it's going to be 14.5. Right?
Exactly.
Okay.
Oh, that's cool.
Yeah.
So that's, you got one of the newer ones, right?
Yeah, they came out with the new software.
Yeah, dude. I'm jealous.
Is there any way to update that?
I'm pretty sure you can't.
Yeah, you can.
You can update the old
Yeah,
ones?
the software is free on their website.
Oh, sweet. I'm gonna go do that.
They've got you can now put the ratios
Like
I know,
fractions
they
and
look
stuff,
like they're
yeah.
supposed to.
Yeah.
Exponents actually go up instead of the
Exactly.
stupid little caret. Yeah.
So nice.
So if you guys have a connection from your TI to the computer, if you go to TI website, it sounds like the new software is awesome because it actually makes the things look like they're supposed to. Exponents go up. Square roots cover the whole thing. You don't need parentheses. It just covers the whole damn thing. It's really kind of nice.
Is there like a plug?
Yeah, there should be a plug on the end. Do you see it?
Yeah.
Cool. And you have to get a little connection, USB connection for your computer. Yeah.
I'll plug a carrot. So do we have to set up an N, a P, and a Q for each of the things for 1, 2, and 3?
N, P, and Q won't change for a given problem because I'm flipping it 14 times no matter what. So that's N.
Yeah.
P and Q are both going to be
50.
50-50, yeah. The only thing that's changing from A, B, C is X, the number of successes. Do you need the original CD? Oh no, I don't think so. You should be able to connect it. You download programs from the website directly. I don't think you need any. Do you need driver software? I don't think so. Should be plug and play. So I think the only one that's really going to be maybe strange is that last one. What are you getting for the first one, for part A? Good. So here, this is the reason why I put this over here, because this is the same all the way down. There's 14 trials, 14 times I'm doing something, 50-50 for the probabilities. That doesn't change. And then for 9 heads, it would be, yeah, 14 C9.
0.5 over 9.
Yeah, 0.5 to the 9th, right?
Yeah.
And then times 0.5 to the
5.
5. And some of you guys are a little better with understanding some of these numbers. You realize these all end up being 0.5 to the 14th. If it's 50-50, what's 0.5 to the 9th times 0.5 to the 5th? 0.5 to the 14th. So you kind of make this a little quicker, but it doesn't really change anything. What do you get when you put that in there? 0.122. 2. Cool. And then this guy's going to look like 14 choose 1. Cool. 0.5 to the first, 0.5 to the rest. And what do you get there? 8.5449 e to the negative 4. And what's that look like as a decimal? Good. So 0.0009 or 0.0001. 0.01, really?
3 zeros.
Oh, it's 3 zeros, yeah, thanks. Because what's that E negative 4 mean?
10 to the negative 4.
Times 10 to the negative 4, so you got to move the decimal back 3 times. The nice thing with negative scientific notation is it's just one less zero. So you have negative 4, you have 3 zeros in front. And then more than one head. How would you do more than one head? If you did it directly, that would suck, because you have to do for 2, 3, 4, 5, up to 14. That is not good. What's a better way to do this?
So we're not including P0.
I like it. So 1 minus the probability of none minus what other probability am I leaving out? More than 1 does not include 1. So the semi-nice thing here is I already know what probability of 1 is. We already calculated that here, right?
Mm-hmm.
So I don't know if you picked up on this, but I like to do that. You've already done some work you need later. The only thing I haven't done yet is probability of no heads. So what would that piece look like?
0.5 to 13, 14.
Yeah, it'd be 14, choose none, 0.5 to the
14.
none, and then 0.5 to the 14th. Of course, I know some of you guys realize that's more than I really need there, but you know that's what the whole thing looks like.
Mm-hmm.
So what do you get when you do that?
6.1 times 10 to the negative 5th.
6.1 times 10 to the negative 5th.
Mm-hmm.
So let me just put in there e negative 5, and that's going to be 0.123461. Pretty damn small, right? So to get the probability of more than one head, then I can do 1 minus none, which we just got was 0.00061, minus 1, which we got earlier, 0.0009 roughly, right?
4 0. Add 0 to the 6 1.
Oh, thank you, thank you. Cool. How are we doing there? It's a lot like the at least 1. At least 1 is 1 minus the probability of none. Well, more than 1 is going to be 1 minus what leaves off. What leaves off is none or 1. So I got to subtract both of those. So let me try this again.
That was really fast.
Let me put it up here. It might be a little easier to see.
Can we add the subtract together and minus the 1?
Say again?
Can we add subtract together and minus 1 time?
Can you subtract?
Add subtract with be more owning, right? And then you subtract from 1. Can you do that too?
Oh, add 0 and 1. And then subtract from 1. Is that what you're saying? Right. Sure, of course. Yeah. More than one head would be too much work. The opposite of more than 1 is less work. The opposite of more than 1 is 0 or 1. So I can do 1 minus probably a 0 or 1. That's what that must equal. Because those are opposites of each other. Right? What's the probability of 0 plus the probability of 1 plus probability of more than 1? What's that got to equal?
1.
Why? Because that's everything, right? So then how do you solve for this? You subtract these two, don't you?
Mm-hmm.
The probability of something is 1 minus the probability of the opposite. If the probability of what they're asking me involves a lot of work, let me look at the opposite. Maybe it's less work. If it's less work, I'll do the less work. You can always do that with probabilities. It won't always be less work, but if it is, I'm going to do the less work. So that's how I can get to what I'm asking. Instead of adding 2, 3, 4 and doing all that calculating, let me not do that. So here I get 1 minus none we figured out was 0.000061. And 1 we figured out was 0.009. And what do you get when you subtract those?
You're missing a 0.
0.999.
0.99.
90.
Did I leave a 0 out?
Yeah.
Of course it did. So roughly 99.9%. Cool. Okay. All right, so that one was the hardest problem up there, but I'm hoping you guys are starting to realize the opposite of that probability involves less calculations. So hell yes, I'm going to do that because there's less to do. Okay. So let me put that that up here. Okay. So now notice what's happening down here. In the book, and we're really not going to use this table much, but they do refer to it a couple times in the homework, just to show you there's another way to kind of show you binomial probabilities. There's a table in the book, and actually I just copied this from that table. If you look at page 611 in the book, there we go. Oh, it's not 611. It was earlier, just, where is it? Here we go. Page 606. Nope, sorry. Before that. It's page 601. So it starts there, and you guys see how it kind of runs by number of trials. So on page 601, you see it starts at n equal 2. So what's the most successes you can have if I'm going to look at something, I'm going to do something twice?
2.
I can have at most 2 successes. That's why x only goes 0, 1, 2. Oh, there it is. Okay, cool. All right. So it starts here. So for 2 trials, I could have 0, 1, or 2 successes. Here are the probabilities they allow me to have to use the table. So when is a really easy example of when I wouldn't be able to use this table?
1.
What do you mean 1?
I mean, for more than 2.
Well, for n equal to 1, it's kind of arbitrary. It's kind of easy to do the equation anyway. So they didn't put n equals to 1. More generally, could I do it if I had a probability of success of 4.2%? No, I can only do it for 1%, 5%, 10%. Right? So the table is only good for very specific situations. Are you guys with me? Mm-hmm. So the table, that's why we're not going to use it much. Because not all of our situations fall so nicely into nice whole numbers or something, right? But for this one, it'll work. Because we've got a 50-50 chance here for flipping a coin. So if I go to 14, N14, that's page 603. I can have 0 up to 14 successes. Cool? Oh, what happened to you? Oh, you're good. And then if I look at P of 50%, my probability of success is 50%. So if I look down, there's all my probabilities there. Okay, so I just want to real quick show you where I got this from. Okay, this here is just directly from there. And so just to double check, what does it say in the table for exactly 9 heads? 0.122. So they rounded to 3 places in that table. Okay. And for 1, we got 0.0009, which rounds to 0.001, and that's what they got there for 1. Mm-hmm. Who knows what 0 plus might mean?
Small positive number plus.
Yeah, what are they trying to make sure it's understood? If they just put a 0 there, what would I think? It can't be done, and which is not true. You can certainly get 0 heads. It's just really unlikely, right?
So when we put it in our calculator, we just put a 0, right?
Yeah, when you put it in your calculator, you can just put a 0. Okay. If there's a problem that says refer to the table, just count that as a 0. Yeah. All right. So now, do you see how this should look very familiar? What's this? Histogram. This is a different kind of histogram, though. I want to make this point right now. This is going to come back to get us later. 3 is right there, right? And 3, of course, is 0.022. But what does 3 go from to, really? Good, 2.5 to 3.5. That is going to be incredibly important in the last section of Chapter 6. We're actually going to come back to this when we get there to do some problems with this data again, right? But for right now, do you guys see how a question like that last one, more than 1, is very simple when you have all the probabilities, of course. Because then you can just add them all up. You don't have to worry about 1 minus. You can just take 2 plus 3 plus 4. It's pretty quick. What's the probability at most 6? How would you do that from just looking at the picture? How would you get the probability of most 6?
Add the 6.
Yeah, add 6 and all the ones below it, right? What does this image look like, of course? What shape does it have?
Bell curve.
Bell curve. What is it about the data, the way that I gave us this binomial, what is it about that that tells you it would probably be symmetric like this? Really nice and symmetric distribution.
This would be normal.
What about it though? In fact, look at the book again. Let me show you this here. This is really important here. That looks very normal. It's symmetric. It's perfectly symmetric, isn't it?
Mm-hmm.
Yeah. So it looks like a really good possibility for being normal. What would it look if I would have made a histogram out of, if it was P of 0.05 instead of P of 0.50? Look at the 14 now. Does that look like it's going to be symmetric?
No.
In fact, that's going to be start off high and go down from there. Why is the middle one the largest when P is 0.5? Why is 7 the largest probability? When I do it 14 times and it's a 50% chance, what's the average? How many heads do I expect to get? 7. And of course, it's called expected value because it should be the highest probability. It should be the most likely thing to occur. So that's why that's the highest. When it's P of 0.05, does anybody know what the average would be then? If I was doing something 14 times, there's only a 5% chance of happening. How many successes do I expect then? What's the average formula that we talked about last time? It's the coolest average formula yet. NP, right? In fact, think about it. That's not how you got 7, but it actually is. How did you get 7 earlier? Because you took 14 times 50%. 14 times 50%. So how do you get it now if P is 0.05? 14 times 0.05. Good. Which is just be one decimal back, 0.7. So the most likely thing to occur is less than 1. And where's the highest bar if it's 0.05? Where's the highest bar? 0. Because then the most likely thing to occur then is between 0 and 1. You guys kind of with me here? Mm-hmm. The highest bar will be on the mean. So if the probability is too low, the mean is going to be slammed up against the side like this. If the probability is too high, the mean is going to be slammed up on the other side. Are those going to be symmetric? So what really makes the mean right in the middle here is because the probability is 50%. So if the probability is like 40% to 60%, you have a really good chance to be symmetric. All right, so we're going to talk a lot more about what makes a binomial normal when we get into the end of chapter 6. I figure I'll bring it up right now. Okay. So coming back to this, just to finish out a couple things. Okay. Blah, blah, blah. What's the whole area that's going to be, of course? The whole area of this picture is 1. So I'm trying to transition us into chapter 6. If I know what the areas are of these shapes, I can just add them up. And the funny thing about these, what is the area of like this one? How do I get the area of this shape? And what shape is that?
Rectangle.
Rectangle. So the height, how tall is it?
So it's
0.061. And how wide is it? 1. So what's the area? 0.061. That's crazy. So if I have a nice shape, like a triangle or a rectangle, if my distribution happens to be a nice shape that I can do, I could just use geometry to get it. A normal curve, is that a shape that I know the area of? If I draw a normal curve, do you guys know the formula for the area of that? For that section, let's say. No, it's got a freaking curve at the top. It's not a rectangle. It's not a trapezoid. It's a straight curvy dude. What the hell's that? So in chapter 6, we are dealing with figuring out little pieces of a normal distribution. Let's say I want to know the probability some dude is between 60 and 66 inches tall. I want to know that probability. Well, I got to calculate the area of this, like we just figured out. I've got to know the area of that. And thank God somebody else did it for us, because it involves calculus, right? Calculus is all about finding areas below curves. We're not going to get into that crap. We're just going to use the table that they made. I'm not going to teach you calculus. Don't worry. Okay. This last little thing, let's try this last little thing out. So we already know this. 14 times 0.5 is 7. Figure out the variance in the standard deviation real quick for me.
It can't be negative, right?
No. So the variance would be n times p times q. So it should be
3.5 over
14 times 0.5 times 0.5, right?
square root.
So what do you get for that?
3.5.
3.5. That's the variance.
1.87.
Beautiful. And the standard deviation would be the square root of 3.5, and you get what now?
1.870.
1.870?
Or
No,
1.871.
1? Okay. So again, you do n times p times q. That's the variance. And we know the standard deviation has involved somewhere square root. So take the square root of that. And that's my standard deviation, 1.871. Now, who remembers how to get this minimum expected number of heads and the maximum expected number of heads? How far out do you have to go before it becomes unexpected?
2.
2, right? It's unusual outside of 2 standard deviations away. So take the mean. The mean is 7. Add 2 standard deviations to it. Subtract 2 standard deviations from it. So what do you get here? Like 10.742.
742.
And down here you get
3.528.
3.258. So with 3 heads, bless you, with 3 heads out of 14 tosses, would that be unusual? Yes, because it's below the minimum expected, right? And the same thing, if I said, would 12 heads be unusual? Yes, it would be. Right. Cool. Okay, maybe. So this is what you're going to see in the homework, in that section, that last section out of chapter 5. They want you to get the mean, the standard deviation, and tell them the minimum expected and the max expected. And then they're going to say, well, is this unusual? Well, you see, does it fall inside or outside? If it's in, it's usual. If it's outside, it's unusual. Cool. Now here's the last little thing I want to say up here. What percentage should be in between those two? What percentage should be in there, considering this looks pretty normal? 95%. So it's roughly 3 up to, what was it, 10? Almost 11, right? So somebody help me out. What is this plus this plus this plus this plus this? Add up from there to there. What would that be? 6.9? pretty damn close to 95. And in fact, it's a little mean for me to go from here to here, isn't it? Why is it mean for me to go from here to there? It's sort of mean because 3.2, I really should start from here and go up to 10.74. So if I did that, it would actually be even closer to 95%. All right, how are we doing?
So do you include the 3 and the 10 or no?
In that case, I didn't include them because officially 3 is not really in there, right?
So you just went from the 4 to
Yep. That by itself was pretty damn close to 95%. And the reason it wasn't exactly 95% is because we were actually, like I just said, like you just realized, we weren't really including everything that I should have, right? Okay, how are we doing? Okay. So it's nice. It's something we've been talking about since almost day one. Normal curve, what's it look like? And then we started talking about what should a normal curve do? Well, it should have 68% in here, 95% in there, and there. That looks like a damn normal curve, and it does have about 95% if I go out 2 steps. That's kind of cool to see that happen. So, now we're going to get into chapter 2. Chapter 6. Hopefully, this will have helped you understand a little bit more of what we're going to do in there. Okay. Whoa. So what we do in chapter 6 is, don't want to kill that entirely. We kind of fill in the gaps that the empirical rule leaves. And the empirical rule has gigantic gaps in it, right? I can only say within 1, within 2, within 3. So if, for example, I know that men have an average height of 69 inches and a standard deviation of 2.8 inches, I think it is roughly. And I want to know what percentage of men will have to duck when they go through the door back there, right? I think in one of my classrooms we actually measured the door and it came out to be 76 inches tall, I think. So I wonder the probability that somebody will have to duck when they go through the door. So that person would have to be how related to 76 inches? They'd have to be taller than that, right? Now, do you remember what it was about heights? Are heights normally distributed? Are heights of men normally distributed? Who remembers that? What should they be? There should be most men in the middle, and then it kind of goes down from there. So yes, they are normally distributed, right? So if I drew this situation, what goes right in the middle? 69, I love it. Where does 76 go? Because that's the point that I'm interested in. Of course, it goes up here. For some reason, I always get people that can get themselves confused because they put stuff in the wrong place. This is a number line. Put it in the right place. 76 is up here somewhere. Where's the area that that problem talks about? Much like the area we were talking about when we were looking at the histogram that I had up here earlier. Where's the area that that talks about? Yeah, greater than. So it's got to be here. So in chapter 6, those are your first steps. Take the information I told you, draw a picture, put the mean in the middle, put the data point or points that you're interested in on there also, shade in the question. So here's what the question looks like in math. Here's what it looks like visually. It's much nicer to have a visual representation of what the hell's going on. Now, what did we have to do to use empirical rule? What are those 1, 2, 3? What do they really relate to? Within 1, within 2, within 3? Even better than standard deviation. Something that uses standard deviation to tell you how far away you are. Z-scores. So what would the Z-score be for this? Yeah, so somebody's already got that? So what's the formula? How do I use that? So it's going to be x minus the mean divided by
2.8.
I like it. So the 76, my data point, minus the mean,
69 over
divided by 2.8. What do you get there?
0.5.
2.5? Now, does the empirical rule say anything about within 2.5 steps? Doesn't say a damn thing about it. So it kind of lets us down. I can't use empirical rule. I need to use something a little more beefy, a little more fill in the gaps, something that tells me more than just 1, 2, or 3. And if you have a new book and you haven't ripped it out yet, there's an insert in there somewhere. In the early, I think it's in chapter 2 or 3. Right, there you go. So if you've been looking at the insert and wondering what the hell it is, now we're finally going to talk about it. Let me wake everybody up here. If you don't have the insert, you just go to the very back. Just open the very back. Oh, there it is. Right. So we're looking at the z-score. The insert has got crazy amounts of stuff in it. In fact, it's a really nice reference for formulas, right? Well, what I want to look at right now is the z-score chart. Someday. And the hardest thing at first is to figure out how this thing is organized. Right? When you first look at it, how do you look stuff up in it? It's a little weird how it's organized. Let me see. So the way that they pretty much had to organize this so they could fit it all. It's really ugly looking. Alright, anyway. Notice how there's my z-scores out here. In here are probabilities, otherwise known as areas. So that's a big point I want to make right now. For a distribution like this, the area is the same thing as the probability. Sort of like when you're playing darts, which I don't play very often at all because I suck at it and I hurt people. The reason that they have those, that you get so many points when you get the little bullseye is because it's such a small area. It's such an unlikely thing to do randomly, right? So the probability you'll land in there is about equal to the area of that thing. If you're really good, though, you can get it in there because that's a measure of your skill. That's evidence that you're not just randomly throwing it and getting it in there. How are we doing? So area does directly relate to probability. Where's my 2.5 z-score, though? So here's my z-scores. 2.5 is here. And then which one of these is the answer, though?
What are we looking for?
Let's try it. Okay. 2.5 what? What was the next decimal place? Was it exactly 2.5? Who still has that in there? Was this exactly 2.5?
Yeah.
Yes, cool. So it's 2.5, 0. As opposed to 2.51. So here's 2.5, 0. Where's 2.53? 2.53. Do you see how this is the first decimal place, and then you go across for the second decimal place? And now some of you guys might realize that's why earlier I was saying z-scores are going to eventually take them out to 2 places because the chart takes them out to 2 places, right? Now, we'll also show you how to do this in your calculator because the calculator will be a lot more precise. But I and some of my colleagues still think there is used to doing this, so you guys kind of get used to where things fall, how quickly the probabilities change as you move along here. Notice how quickly they change up here when you're really close to the mean, 50% below the mean. Then it goes up by 0.004. Notice how little bit they're changing here. They're not changing very much here at all, right? Because then at that point you're down where it's really tiny. So you take a little step and you're not really adding very much. Okay.
but not equal 0, right? In the bottom one.
Say again?
Say that the bottom one is not going to be equal 0, right?
Yeah, when you get to the very outsides, they would be close to 0, right?
Not cuts at 0, right? In the bottom one, the bell.
On the very outsides, they get close to 0. Yeah, cool. But now notice this about this. Whenever you look up a z-score, what area does it give you? Always. the area that is
No.
below, right? So if you look up 2.50, we get an area of 0.9938. Where is that on my picture?
Below 76.
It's here. Which makes sense. This is like 99%. If you said this was 99%, that doesn't make a damn bit of sense. That tiny little bit is 99%. Doesn't make any sense. So how do I get my answer then?
Subtract from
1
1.
I love it. 1 minus that. 0.0062. Okay. Slowly but surely. So let me give you a couple of more direct questions about how to use this chart. Figure out these probabilities just by looking at the chart. So like the probability that z is less than negative 1.41. So there's a whole negative side, right? Probability that z is greater than 0.14. And then finally, the probability that z is between negative 3.01 and 1.92. Yeah. What are you guys getting for this one? The less than negative 141? So if you look up negative 141, the chart's going to tell you the area that is below it, right? So if I drew this out, here's my 0, here's my negative 141. I want the area below that, less than that. So what's the chart tell you?
0.0793.
Yeah, so 0793. That's right there. 0.0793. Oh, where'd you go? 141. Shoot. There. 0.0793. Greater than 0.14. So I want that area there. So when I look up 0.14 in the chart, what does it tell me?
0.5557.
Good, so 1,4 is right there, 5557. The minute you look up something in the chart for these problems, you put it in the right place. If you've drawn your picture, you know if you're done or not. So when you put 0.5557 there, you know you're not done. Because visually the question is right there. So again, now to get that, you just have to 1 minus this, 4443. How we doing? Real quick, before I go to the next one, just to show you guys, if you don't quite understand this yet, you might eventually. If you never do, it's okay. Look up negative 0.14. What do you get?
0.4443.
Which was our answer, right? Because negative 0.144 should be the same area as this. So it's because of the symmetry of that. I can look up the negative z-score. You got to be real careful that you totally understand that shortcut so you don't do it at the wrong time. If you don't understand the shortcut at all, who cares? It's not that much more work just to do 1 minus that. It's not a big deal. I figure I'd tell you that right now. Now, how in the world do I do part 3? It's got 2 questions to it. So here's the area that I want. If I look up 1.92, that's going to be too much, right? Because it goes from 1.92 all the way down. I want to go from 1.92 and stop at 3.01, right?
So minus.
I love it. So I heard somebody say that earlier. That's exactly right. You find this area, and you subtract them. That will end up with the area in the middle. That really only makes sense. If you take this whole thing minus this piece, it will leave you with this in the middle, which is exactly what you want. So what do you get when you look up 1.92? 9726, I love it. And when you look up negative 3.01?
0.0013.
0013, cool. So you do 0.9726 minus 0.0013.
0.9713.
I love it. Cool. So 97% chance of being in there. I like it. So basically what we just did, just to merely make sure you guys understand this, because I really, this is one thing I don't like about this book. Section 6.2. Section 6.2 talks about temperatures all the time, but they have a mean of 0 and a standard deviation of 1. So if you convert those to z-scores, won't they be the same? They have a mean of 0, and a standard deviation of 1. So those are really z-scores they're giving you. So in section 6.2, it's problems like this. All you got to do is look it up and then subtract or add depending on what you have to do to get the area you want. That's 6.2. 6.3 is actually more like the one we did first. 6.3 just adds one extra step. It doesn't give you z-scores. It gives you heights or SAT scores. You've got to convert them to z-scores and then look them up. So in next class, I'm going to have a handout that I'm going to let you guys work on in groups that deals with a whole bunch of problems like this to make sure we all get it down, how to do this. Cool. And of course, we'll have the earthquake drill then.
Can you bring the quiz on Thursday?
Can you do...
Can I bring this because I told you I